Hello everyone and welcome to this introduction course to Bash shell scripting. This course is aimed at anyone who is new to shell scripting, people who want to expand their knowledge, or for those who want to refresh their knowledge. My name is Herbert and I will be your instructor for this course. I've been in the IT sector as a system engineer since 2009. I've dealt with multiple systems ranging from Windows Server to Linux servers, and in the last few years I started specializing in automation and development. I've been doing YouTube content creation since 2017 up until now, and I've already created a course on Linux, which might be a good starting point if you're completely new to Linux and want to learn more about the basics of the operating system itself. Now, what is Bash? Bash is short for Born Again Shell. It replaced the Bourne shell in the GNU/Linux project, which was the default shell for Unix operating systems. A shell is a user interface for ease of use. It makes it easy for the user to manage the operating system without knowing all of the inner workings and complexity of the operating system itself. Now, why would you learn Bash? Well, the reason you want to learn Bash is because it's currently the most popular shell scripting language for the Linux operating system. Bash has been around forever. It has been used since the early days of Linux, and it has stood the test of time ever since. It's also included in macOS and in Windows when you're using the Windows subsystem for Linux. Now, why would you not use Bash? Well, even though Bash is considered a programming language, it obviously lacks some features. For example, the ability to do object-oriented programming is not available in Bash. Python would obviously be the preferred choice here if you're looking to create more advanced scripts that allow object-oriented programming. Speaking of Python, Bash is also more complex in its syntax. When comparing Python syntax to Bash, one could say that Bash is a lot harder to read and write. Not only Python is often a better choice for more advanced scripting, newer tools like Ansible also make it a lot easier for you to manage multiple systems, which is a lot harder to do with Bash. Of course, Ansible and Python are often overkill for simple scripts, and using one does not exclude the other. Bash is often used in tandem with tools like Ansible or integrated in Python scripts. This is exactly the reason why you should learn Bash. Just knowing the basics could mean a big difference in a lot of situations. Sometimes the old trusty tools are still the most reliable. What will you need for this course? I aimed this course at the standard Windows user. So I built the course around the Windows subsystem for Linux, aka WSL. Since we will be only using command line tools and no GUI, WSL seemed like the obvious choice, and I also have a video explaining how to install WSL on Windows. If you're running a true Linux distro, even better. If you're using a Mac, you can follow along in your terminal window, but first make sure that you have Bash set as your preferred shell. Small disclaimer, basic Linux knowledge is required. If you're completely new to Linux or even new to Bash, I would suggest you at least follow along with the Linux guide that I have on my channel. It's going to give you a good basic understanding of how the Linux operating system works. Before we start with actual scripting, let's first do some basic commands in the terminal. Let's look at an example of two very simple commands to display text in the command line. The first one is called echo, which will display the text you pass it as an argument. We will write the command echo and then we pass it some text, like so. We just type in echo hello, and so we can dissect this by looking at echo as the command and hello as the argument. We will learn more about arguments later in this course. In this case, we talk about a positional argument. Now we can see the output that says hello, which is the word we gave it as an argument. Let's try and see how another command, the cat command, compares to this. The cat command displays the contents of a file. But right now, we don't have one, so let's first create a file with our text editor, Vim. In this course, we're always going to be using Vim, because it's a good text editor that comes with almost all Linux distributions. Plus, it's actually not that hard to use if you get the hang of it. I myself have written multiple scripts in Bash and Python with Vim, so it's definitely a good text editor unless you want to start writing some serious scripts or software. In that case, a decent GUI text editor like VS Code, Atom, or Sublime are better options. Let's create a new file with Vim by typing vim textfile.txt and let's write something in it. To write something in Vim, press the I button and you will enter the insert mode. From this mode, you can start writing text. Let's write hello world in this file. Now we press the escape button and you will see that the insert mode is now gone. We have exited the insert mode and we're back into command mode. And once you're back into the regular command mode, you can press the :W to write the file. And this will make sure the changes we made are actually done and saved to the disk. And then we can press Q to exit the file. Also, to make life simpler, we can go into Vim, make some changes and combine the :W and :Q to write :WQ. This will automatically write the file and quit Vim at the same time. If you made any changes you don't want to save, you can ignore the changes by typing :Q!, which will quit Vim while ignoring any changes made. Now that we created our file, let's try to print the contents of the file with the cat command. This command will print out whatever is in the first positional argument. In our case, it's the name of the file we just created. So we just type in cat textfile.txt and we should see the contents of the file printed here. Okay, great. We can now print our own text and also text files to the terminal. This may not sound like much, but it's something that you will use a lot when writing bash scripts. So now finally, we're going to write a shell script with the knowledge we just gathered in the previous section. Start off by first opening your Vim text editor and name the text file shelltest.sh, like so. Vim space shelltest.sh. Now that we have our text editor opened, let's try another mode of writing text in Vim, the append mode. Instead of pressing I on your keyboard, press the A button. This will append your text rather than insert it. With the insert mode, you write the character before the cursor. With the append mode, you write the character after the cursor. Now in this case, it doesn't matter of course because it's a new file, but I thought I would mention it anyways since sometimes it can come in handy. Let's now start with our shell script. In Vim, write echo hello world and write and quit the file by pressing the insert or append mode, writing echo hello world, then pressing the escape button, and then writing :WQ. Now let's see if we can actually find the file in here using the ls command, which will list all the files in our current directory. As you can see, the file is there and we can verify the location by looking at the terminal's current location over here, which says the tilde symbol, and the tilde symbol indicates that we are in our current home directory. By typing pwd, we can verify that we are indeed in the home directory. PWD stands for print working directory, and this way we can print the directory that we are currently working in, which is indeed our home directory. Now let's run our file by providing the command line with the command line interpreter, which is bash space shelltest.sh. This will output the command we entered in the shell script using the bash interpreter, but when we type in echo $shell, we can verify that we are actually running in a bash shell. So should we really have to specify it? Well, the short answer is yes. Just because we are running in a bash shell, that does not mean that Linux is going to assume every file we want to run is also in bash. We should always provide an interpreter for our shell scripts to use the correct type of shell. That does not mean, however, that we shouldn't make it easier for ourselves. We can actually provide the command line interpreter in the shell script itself by typing it at the top of our script. In our case, we have to provide the full path to the shell interpreter. Let's copy our output from the echo $shell command and use it in our shell script. Copy the output by selecting it and using either Ctrl+C or right-clicking the selection, either should work. Now let's go back into our shell script and let's enter the insert mode since we want to enter all this information in the beginning of the file. Press I and type in $! And then paste in the output of the echo $shell command. And what we do here is we provide the shebang. So the $! is a way of telling the shell script which interpreter to use. We follow up the shebang by providing the full path to the shell interpreter, and this way the shell knows which type of shell interpreter it needs to use. We can now run this file doing period / shelltest.sh. But we will see that permission is denied and we need to give the file permission to be executed. This is because in Linux, we need to give files permission to act as an executable file. Let's have a look at this. When we type in ls-l, which is a long format of the ls command, which is another type of argument we call a flag. So the -l here is called a flag we give as an argument to the ls command. We are actually asking the ls command to provide the long format, which will display some more information about the files and directories. We can see in our permissions that we do not have executable permissions yet. If you want to learn more about the basics of file permissions, you should look at my Linux for Beginners tutorial. Let's give our file executable permissions by typing in chmod or chmod u+x space shelltest.sh. We want to provide u+x because this will give only the owner user permission to execute the file rather than the entire group or anybody on the system. It's good to have this discipline baked into your head, although on a development environment it doesn't really matter very much. Okay, now we can finally run our shell script by typing in period / shelltest.sh, and we will see the output on the terminal. Now that we finally have the basics out of the way, we can actually start writing some bash scripts. To understand a little bit better what variables do in bash, have a look at this script. So in this script you have a classic example of a copy command where we copy something from to a location. Underneath that we have the same location paths twice typed out completely. Now this is something that you want to avoid as much as you can. Underneath that we have a better option where we actually define a location path in a variable called myLocationFrom. Now this is quite a long variable name. You could actually just define something like loc_from, which would be better to make it a little bit shorter, but it's just, it's just for demonstration purposes how this would work. So you could understand if you would have a very long path here, you could have that very long file location stored in a variable, and then you could actually reuse that variable over and over again like we did in the example below that. So let's now have a look at how we can actually use this in an example. So we can either type our name like this, first name equals, let's say, Herbert, and that's how we can actually use these variables by typing like echo hello and then typing the variable like so. So that's how it would work like in line or in the command line itself, but we can actually also just write a script to demonstrate a little bit better how variables work. So just type in vim hello there.sh, and then we'll do the insert mode with the shebang /bin /bash. And then over here, we'll define our first name equals Herbert, or, your name. And then last name equals Lindemans, which is my last name. And then we'll just do like this, echo hello $ first name. And then we'll do $ last name. And then we'll exit with WQ, and now the only thing we need to do is chmod u+x hello there.sh, and now we can run it, and now we can see that our name is printed out here just like that. So now we actually type this statically, but we can actually also ask the user for input like so. So let's open a new shell script with vim interactive shell.sh, and we'll do the same. We'll insert, then we'll do the shebang bin bash, and first of all we'll need to ask the user like, what is your name? So what is your name? What is your first name? Let's ask, and then we'll do a read statement, and we'll read the first name, and we'll do the same with what is your last name, and then we'll read last name, and then we'll echo hello $ first name space $ last name, and then we'll write and quit, and then we'll do the classic chmod u+x and then interactive shell.sh, and we'll run it. And now it's going to prompt us for our first name and for our last name, and then it will just print out our first and last name like so. We could have the terminal display our own name or anything else provided in a positional argument as well. But first, what is a positional argument? A positional argument is exactly what it sounds like. We place the argument at a certain position behind the command or script we want to run. The positional argument can be in position 1, 2, 3, and so forth. The positions are always separated by a space. When working with positional arguments, you expect arguments to be in a certain position that is separated by a space and counting from 1. Position 0 is reserved for the shell itself. Now let's have a look at one of these positional arguments. Create a new script by typing vim posargue.sh and enter the insert mode again. We will have the script take in our first and last name on position 1 and 2, and have it take these words as positional arguments. Let's just write our shebang and write our one line of code like so. Shebang bin bash echo hello $1 $2. Now save the file and close vim, change our permissions, and let's run the script again with the positional arguments /posargue.sh, Herbert Lindemans, or whatever your name is here. And as you can see, we get the same output here with only one line of code. One of the most frequently used features in Bash is piping. It makes it very easy to perform a specific action on the output of the command. Let's say the output of a command is very long and you wish to filter some things out. Piping is going to give you that option. Now, how does piping work? Let's have a look at an example. Let's say we want to look at a specific directory, but we just want to filter out certain files or subdirectories. We could, for example, use a command like this. So we type in ls-l /our directory. In this case, we're using the bin directory at /user/bin, and then space, and then we type the piping symbol, space, grep, which is something that we use to filter out specific words, and then we type in bash. And we'll see the output is just the bash binaries that we can see here rather than the entire bin directory. In this command, we forward the output of the ls command into the next command with the pipe symbol. This symbol represents a pipe, and this is what we call piping. We literally send the output from a command before the pipe symbol to the command behind the pipe symbol. Grep is just an example. There are many more commands that have very powerful potential when used with piping. When sending output to a file, we have to use different kinds of symbols than the pipe symbol. Instead, we use the greater than and double greater than symbols. These symbols will be used to send the output from a command to a file. This can have many potential use cases. The first thing that comes to mind is logging something from your script to a log file, and this is something that you'll definitely use in real-life scenarios. Let's see how we can use these symbols. First, we catch the output of a simple echo command. Start by typing in echo hello world greater than hello.txt. This prints hello world into a file called hello.txt. Notice that we put the command before the greater than symbol and the name of the text file after the greater than symbol. Now we can see if this worked by typing in cat hello.txt, and we should see the output of the echo command in here. Now let's try something different here. Type in echo good day to you greater than hello.txt. And let's see what's the hello.txt file by typing in cat hello.txt. But what's this? The file was overwritten. We don't have our hello world anymore. Well, this is because the greater than symbol always overwrites any existing file. What we need to have is a proper way to append text rather than overwrite it. This is where the double greater than symbol comes in. This will append any output to our destination file rather than overwrite it. Let's try it out, but first let's remove that original file with rm space hello.txt. Then we use echo hello world double greater than symbol hello.txt, and we check if the contents are indeed correct with cat hello.txt, and indeed the text is there. And once we verified this, we send another output to the file using the double greater than symbol and type in echo good day to you double greater than hello.txt. And we once again verify this output with cat hello.txt, and we should see both outputs here. Now imagine using this in combination with timestamps to see which command ran at which time, and also some error handling, and we're starting to collect the tools we need to write a real script. We can also feed input into a command by reversing the greater than symbol. We can use the lesser than, double lesser than, or even triple lesser than symbol to get input from a file, multiple lines of text, or a single string of text. Let's first look at the lesser than operator, which will get input from a text file. We will use the word count command as an example here because it's one of those commands that has a use case for these types of operators. Let's type in wc -w hello.txt to get the word count. But what happens here? We get a little more than we asked for as an output. The wc command by default also shows the file name, which is not what we want. If we just want to get the number of words, we need to feed the wc command an input from the file with the lesser than operator rather than the file itself as a positional argument. This can be done like so. wc -w space lesser than space hello.txt, and this way we will redirect the file to the wc command rather than passing it as a positional argument to the command. We will now get to the second way of feeding data to a command with the double lesser than operator. This is a great way to supply multiple lines of text to a command. When we write the double lesser than operator, we will immediately follow it up with a word that will open and close the text we want to input. Basically, we tell the command line, hey, wait for this word, and then capture everything I wrote in between the first and second occurrence. Often people will write EOF, but you can write whatever you want. Let's have a look at how this would work. So we type in cat space double lesser than symbol EOF. Now we see that the command line waits for input. So we can keep writing lines of text here, and let's write some text, creating a new line with the enter key, and we'll type in I will enter, write some, enter, text here, enter, and now we close it with the first word we supplied, and we type again EOF. And now we should see the text that we wrote here between the two EOF statements. Now last but not least, we can also supply single strings of text to the command line. This will be done with, you guessed it, the triple lesser than operator. Let's have a look at another example of the wc command we use. By default, wc will either read a file or a command output, but not actual strings supplied as positional arguments. We should feed the command either an entire file or the output of a file with one of the lesser than operator variations. Let's see how we can provide a string to this wc command. So we type in wc -w again, space, triple lesser than symbol, and then we open with double quotes, hello there word count, and then we close again with double quotes, and we should see the word count printed here in the terminal. This is how we can feed a string into a command, and take note that the string needs to be in between double quotes, otherwise it will not work. In Bash, we have a built-in command called test that will take in a couple of arguments and show you if the expression is true or not. For example, we can ask the terminal to show us whether or not a string of text is equal to another. We can write test followed by the expression, but I prefer using square brackets. Let's see how that's done. So we just write open square brackets, space, and this is important because you need the space in between, hello, space, equal sign, space, again hello, followed by another space, and then closing the square brackets. And this will show no output, but when we do echo $? We should see output 0 here because the first string of text is equal to the second, and that will give us a return value of 0. $? Returns the value of the exit code of the last executed command. We will learn more about exit codes later. For now, it's enough to know that exit code 0 means that the command was executed without any issues. Another example of this would be comparing numbers with each other. For example, again, we open the square brackets, space, 1 equals 0, space, we close the square brackets, and then we do echo $? And this shows us that the values are not the same because we get a return code 1. But we could also use a different operator here to make sure that the values are actually numerical. We could use the -EQ operator for this. And we do this with opening the square brackets, 1 -EQ 1, close the square brackets, echo $?. This also shows us the same return value, exit code 0, which means that the values do equate. Though this would throw an error if you would use alphabetical characters instead of numerical ones. Now for some more powerful stuff. We can actually use these test expressions and perform an action on it. Let's have a look at this more closely with an actual script. Let's create a login script, which will not really log us in, but it will show us what is possible with these if, elif, else statements. Create a new script called if, elif, else.sh. We type in the shebang. We do if, open the square brackets, $, open curly braces, 1, comma, close curly braces, and I'll explain to you what this means in just a second, equals your username, close the square brackets, semicolon, then, and then we follow up what we actually want to do here. So we want to echo, oh, you're the boss here, welcome. Then start a new line, elif, open the square brackets, again, $, curly braces, 1, comma, curly braces, equals help, close the square brackets, semicolon, then, echo, just enter your username, duh, else, echo, I don't know who you are, but you're not the boss of me, and then close it with fi. Now let me explain to you what we did here. So this script will take in a positional argument, which is a great way to test how the if statements will work. We start our if statements with an if, followed by the test expression. Take note of the square brackets used in the previous section. We test if the first positional argument is equal to the value we provide. Take note of the double comma and the curly braces. This is called a parameter expansion, and it will allow us to ignore upper and lower cases when comparing the two values. We then end the test operator with a semicolon, and we follow it up by then, and then beginning a new line. And on this line, we type what we actually want to do with set test expression. In this case, we just print something out to the console, telling the user the script has recognized the username and that he is indeed the boss of this system. We can also have a script check for multiple test expressions. We can define this with an elif statement. This stands for else if, meaning that else if the previous statement wasn't true, test if this is true. Again, start a new line. We define a test expression that will test if the positional argument is help, and if it is, we display a message that shows us instructions on how to use the script. Being an easy script, we want to state that it isn't so hard to use. Maybe a little rude, but it's all in good fun. Then, if none of these statements are true, finally we have the else statement. This will perform an action if none of the if or elif statements are true. We can display a message saying that the username was not detected and that the system will not be bossed around by someone that does not have the correct username. Finally, to close our if statements, we end it with fi. This closes the entire block of if, elif, else statements and is required. If, elif, else statements are useful, but you won't use them very often if you want to check for multiple values. For these kinds of things, we use case statements. First of all, what is a case statement? Well, a case statement performs different actions depending on which case is true. This means that we can define multiple options, and if the option matches the case, we will perform an action bound to that option. Let's have a look at how this works in a real script. Let's try to recreate our previous exercise with a case statement instead of the if, elif, else statements. Create a new file with vim login.sh and type in the shebang, and then we start our case statement by typing in case space $, and then the variable expansion with the curly brackets 1, comma, space in. And over here, we're going to do something special. We're going to define multiple options. Now, this is something that you could also do with if statements, but I'm just introducing it here with the case statements since I thought it would be interesting to see how it works. So we type in our username, space, and then the pipe symbol, and over here this is actually like a separator for multiple options, rather than the pipe symbol that we saw earlier to pipe things through to different commands. In a case statement, it serves a different function. Over here, it serves as a separator for multiple options. So username, space, pipe symbol, space, and then another username, for example, the administrator. And then we close the bracket, and then we define what we want to say or do here. So you want to say something like, oh, you're the boss here, welcome again, like we did in the previous exercise. And then we close this option with double semicolons. Then we define another option here, for example, help, like we did in the previous exercise. We copy the same echo command, then we close that option with double semicolons. And then what we do here is we define this star symbol or asterisk or whatever you want to call it. And this is the catch-all option that we're going to define. And the catch-all option is like the default option when none of the options are true or when no options are given. And then we define, hello there, but you're not the boss of me. Please enter a valid username. And then we close that option with double semicolons and then close that with ESAC. So it's case just reversed. So again, like I said before, notice that we have two options in one line using the pipe symbol. Again, when we use the pipe symbol in one of the case statement options, we can use it to have multiple values to test for. We define our option for help, also define a catch-all or default option, and this is equal to like the else statement like we saw earlier, meaning that if none of the options are equal to the input, we will perform a specific action, and now we can run our script and get the results that we expect. Before we get into looping, we need to first extend our knowledge about variables. We can actually assign multiple values to one variable collected in a list. We call these kinds of variable lists arrays. Let's see how we can actually create this in the command line. In the command line, type my first list equals open brackets 1 space 2 space 3 space 4 space 5 close the brackets. Take note of how we start the array with open brackets, use a space as a separator for each item, and close the array with the closing bracket. Now let's see what the output is when we try to print this array. Just type in echo, and then just like we would with any other variable, space $, my first list. And now we will see that the output is just the first element. And this is of course not what we want. To echo the entire list, we need to specify it like this. Echo, $, open curly braces, my first list, square brackets, @ symbol, close the square brackets, close the curly braces, and this will print out everything in the list. But we can also define which item we want to print like this. Echo, space, $, curly braces, my first list, square brackets, and then over here we'll just type in 0, which is the index, close the square brackets, close the curly braces, and this will print out the first item in the array because we define the index in between the square brackets, and because in bash the first item in the array always has index 0 counting upwards, we will see the first item in the array. But let's say we want to do something else with all these items in the array. We can do this with a for loop. Now that we have created our array, we want to loop over the items in it and do something using a for loop. In our example, we will count the length of each word in the array by piping the item output using echo to the wc command. Don't forget to specify the -n flag in our echo command, because otherwise it would also count the new line characters. Type in the command line for space item space in, $ curly braces, my first list, square brackets at square brackets, curly braces, semicolon, space, do, space, echo, space -n, space, $item, space, pipe symbol, space, WC, space, -c, semicolon, space, done. Take note of how we write the for loop here. We first define the variable item, which will represent each item in the array during the loop. Then we define the iterable, which is our array. And watch how we actually define it in our for loop. We encapsulate it in our curly brackets and add the square brackets, add square brackets after it to make sure we loop over the entire array. Then we follow it up with a semicolon, space, then we type in do, and then we type in what we actually want to perform here. So we'll type in do, echo, -n. As I said, the -n is just a flag for the echo command to ignore all the new line characters. And then space, $item, because the $item will represent one of the items that we are currently looping over, space, and then the pipe symbol, WC -c, and then we do again, semicolon, and then we type in done. To understand why we need functions in a bash script, we should first consider this. In some scenarios, we have a lot of repeated code. We might want to do a specific set of commands in a certain order, or we want to run data through a set of if-else statements multiple times. For these scenarios, we create functions. These functions are like little programs within your script that you can run from within your script. It makes it so that you can make your code reusable. Very powerful stuff, because we can save so much time and lines of code. Let's write our first function in bash. Let's open up a new file called firstfunction.sh. I will type in the shebang, and then a new line. We'll type in the name of the function. I will just call this show uptime. And then we open and close the brackets. And then we open the curly brackets. We'll type in up equals $, open brackets, uptime -p, pipe cut -c4 minus, and then close the brackets. We'll type in since equals $, open brackets, uptime -s, close the brackets. And again, if I'm going a little bit too fast for you, you can pause the video and I'm going to go over what we actually did here. I'm going to dissect everything we did here in just a second. And then a new line again, cat, and then we'll use the double lesser than symbol, EOF, and we'll type a new line, and we'll just create something pretty here, a few dashes, and we'll type in this machine has been up for $ curly braces up curly braces. It has been running since $ curly brackets since curly braces. Then a new line of, then we do a new line of dashes. Then we end our statement with EOF, close the curly brackets, and then we just type in show uptime. So let's dissect this again. First, we define the name of the function, followed by open and close brackets, followed by the curly brackets. To define what our function does, we enter all the things it needs to do in between the curly brackets. In our case, we will show the uptime of the machine, watch how we catch the output of a command into a variable using the $brackets notation. Then we do this again in the next variable. We define the variable in the same way, but we use different flags for the uptime command and store that output in the since variable. And we can now create a nice output using these variables using the cat command and the redirection we learned earlier in the course. We end by closing the curly brackets, and then we call the function by just typing it anywhere in the script. As long as it's typed under the function, it's fine, because we need to make sure that the function first is defined. When we define a variable in our function, it's available to the entire script by default. This might seem okay, but it can actually cause trouble when you write bigger scripts. We want to define the variables inside our functions as local variables so that they are only available to our function and not to the entire script. This way, we will avoid accidentally overwriting global variables, which might cause issues when we are using functions that share these variable names. Let's have a look at what happens when we don't use local variables. So let's define our variables named up equals before, since equals function. And then we'll just print those out before we define the function. So we'll just echo up and echo since. And then now we will define the show uptime function again. and we will leave it the way it is, and then echo up and echo since. And let's run it, and in this example we can see that the variables are indeed globally available, which is not what we wanted. We'll see also that they are globally available, but we have actually overwritten the variables that were defined before the function, and then the function was actually reassigning those variables because they are not assigned as local variables. Let's fix that. So the only thing we need to do to fix it really is just add local before we define the variable in our function. So instead of just writing up and since equals the commands that we want to use, before the up, we'll just enter local space, and then the same goes for since. We'll define local space. And when we run this, we can now see that our variables are available to the scope of our function, but the global variable is not overwritten. Just like our entire bash script can have a positional argument, so can our function. Let's have a look at an example. Create a new script called function posargue.sh, and we'll write the shebang. And then we'll open our function with the function name, open the brackets, open the curly brackets, and then we'll write echo hello $1, and then close the curly brackets, and then we'll write the function name space, and then whatever you want to write here, we'll write our own name. So we can write out whatever set of characters we want, but in this case, we wrote our own name. We could even go as far as to pass positional arguments of the entire script to the positional argument of the function. And of course, functions can also take in multiple positional arguments, so lots of stuff is possible here. Let's open up the previous file. Underneath the echo statement, we'll type an if statement, and then we'll say if $curly braces 1, equals, and then your username, which in my case is Herbert, close the brackets, semicolon, then return 0. Else, we will return 1. And then we'll close the if statement. And then also over here, we'll remove this static name and change it to a positional argument 1. And then also if $question mark equals 1, and close the square brackets, semicolon, then echo, and then it will write someone unknown called the function. And then we'll close the if statement, and we'll write and quit. And let's now try to run this with test, for example. It'll say hello test, but then you'll see that it also says that someone unknown requested the function. AWK is one of the most useful tools in the bash arsenal. We use AWK to filter file contents or the output of a command in such a way that we can print out the most essential parts and get the output the way we like it. To use AWK, we can either filter parts of a file or we can filter parts of a command output by piping that output into AWK. Let's have a look at how we can filter through a simple text file with AWK. We first create a test file which contains 3 words separated by a space. Once we created that file, we can put AWK to work. Type in AWK, single quote, open the curly brackets, print $1, close curly brackets, single quotes, space, the name of our test file. We will see that the $1 acts as a placeholder for the first item in the text file. We could also get the second word that comes after the first word, always separated by a space, by typing in AWK, single quotes, curly braces, print $2, close curly braces, single quote, and again our test file. Now that we get the idea of AWK in its default mode, which is using a space character as a separator, we can move on to changing it into other characters, such as a comma. Let's create a CSV file and add 3 values in it again, separated by a comma this time. Now we can use AWK again to split the values in the CSV file by adding the -F flag and specifying the split character afterwards, like this. AWK -F, comma, space, open the single quotes, open the curly braces, print $1, close the curly braces, single quote, test csv.csv. And now we will see that the output is also the same as in our previous examples, but we will see that AWK actually used the comma as a separator character. And last but not least, we can also pipe commands into AWK, like so. Type in echo, just get this word, hello, and then we pipe into AWK, and we'll print out number 5 because this is the 5th word separated by a space. And then we'll see that the word hello will be printed out. Or we can also split this at the colon symbol like so. echo, just get this word, hello, pipe into AWK, and then we specify the -f, we follow it up with a colon, and then print $2, and then we'll still have to cut off the first character, which is a space, and then we'll get the same results as well. And that's just the beginning. Of course, there's a lot more possible with AWK. So if you want to practice, you can try using it more often in your scripts. It really pays off to know this well, because you'll do a lot of output filtering and reformatting in Bash. There will come a time where you want to change certain values in text files, and that's where sed or set comes in. Set is a command line tool that would allow you to modify values in a text file using regular expressions. Let's have a look at an example on how to use sed or set to replace values in a text file. Create a text file called settest.txt and let's write down some text here. Now we will replace the word fly with grasshopper just for demonstration purposes. So we type in set single quotes s/fly/grasshopper/g single quotes and then the name of our text file, which is settest.txt. Now the structure of this command is a little bit daunting, but let's break it down. First, we start off with the set command. We open the single quotes and start our regular expression. First, we enter the mode we want to use, which is S for substitute, meaning we want to substitute the next word behind the / with the word after the second /, which is, the first one is fly, and then the second one is grasshopper. Then after the last, we provide the G, which means that we want to do this globally. G stands for globally. And globally means that we want to do this across the entire text file, which means that we want to change every occurrence. We close it with another single quote and we put the text file we want to change behind the entire command. Let's say we want to keep the original in a backup file. We can do this by adding the -i flag to the command like so. So we just do the same thing, we'll just do set -i dot original, and then we enter the exact same command we just provided earlier. We can see here that we use the -i flag, but we don't put a space behind it. Instead, we write the entire suffix behind the -i flag. This will create a backup file which contains the original content of the file we just changed with the set command, but the original file will have the changes we desired. Just like with AWK, this is a basic introduction to set and there will be so much more to it. But as with all things in IT, you need to discover this by yourself by trying it out as much as you can. Well, this brings us to the end of the course, but if you want to go the extra mile, I have a little bonus project where we will use everything we learned in this course to create our own personal system assistant.